So this is our second question from thermal energy transfer unit, right? So let's look at this. This concerns mainly the calorimetry, right? So if you've read the text, you'll understand what I mean. But the calorimetry method is a method where we fill a calorimeter with some liquid and then we insert maybe ice or some other metal into it and try to see how the temperature varies and basically apply law of conservation of energy to find specific gravity and other things, specific heat capacity and other things. Okay. So let's read the question and see what it's saying. A calorimeter of mass 90 gram and specific heat capacity 420 joule kilogram per Kelvin contains 360 gram of liquid, right? So if I just draw, this is our calorimeter in the first place, right? Its weight is 90 gram. We'll definitely need to convert it into kilograms and specific heat capacity. So C for this is 420 joule per kg per Kelvin and contains a liquid, okay, which is 310 grams, right? And the liquid and the calorimeter right now to start with is at 15 degrees Celsius. Okay, so that's our starting point. We don't know much about the liquid, but we proceed. The electric heater rated 20 watt warms the liquid to 19 degrees in 3 minutes. Okay, so the heat is provided by the electric heater. Okay, and it is of 20 watts, which means it is providing 20 joules per second. Okay, and it is running for 3 minutes. Okay, so whatever heat is going to come inside the system is going to come through the heater. Okay, and we can exactly compute how much heat it is going to be, right? And finally, the temperature is raised from 15 degrees Celsius to 90 degrees Celsius. Okay, assuming there is no energy loss to the surrounding, estimate the specific heat capacity of the liquid, right? So as I was mentioning, calorimeter could be used to find the specific heat capacity of the liquid or solid objects as well. Okay, so it's a very simple application of law of conservation of energy. First, we have to see that this is our initial situation for the calorimeter, right? And the final situation is 90 degrees. Okay, so there's a delta T which is happening is 4 degree Celsius, or we can directly convert into 4 Kelvin. Okay, so we don't say degree Kelvin, we just say Kelvin. Fine. So that's our delta T, right? How much heat is into the system? We can compute that. So in every second, it is giving 20 joules. So in 3 minutes, it is going to give 20 joules, right? Into 3 into 60. Okay. So that is going to be equal to 20 3600 joules. Okay, 3600 joules. So that much 3600 joules energy is going to come in, and that is going to increase the temperature both for the calorimeter as well as the liquid inside. Okay, by how much? By 4 Kelvin. Okay, so we can now see who is going to consume the heat. So this heat will be consumed first by the calorimeter. Okay, and second by the liquid inside. Okay, and this consumption will be exactly equal to 3600 joules, right? So let's see how much heat will be consumed by the calorimeter. So for the calorimeter, we'll need the mass of the calorimeter, which is 90 gram, right? So we are going to apply the same formula. Q is equal to m phi delta T, okay, or m cat we say it, right? So for the calorimeter, right, its mass is 90 gram. So this is going to be 090 kilogram, right? 90 gram into its specific heat capacity, which is 420 joules. So 420 joules multiplied by the delta T. Delta T we have found to be 4 Kelvin. So this is going to be 4. Okay. So that much heat in joules the calorimeter itself will take, right? We can compute that, and that is going to be equal to 151.2 joules, or we can say 151 joules. Okay. Now, how much heat will be consumed by the liquid? The liquid will also consume the heat given by the heater, and that is going to be equal to the mass of the liquid, which is given to it 310 grams. That is going to be 0.310 kilograms, right? And the specific heat capacity of this liquid, right? That is what we intend to find, right? Cl multiplied by the change in temperature, which is 4 Kelvin. Okay, so this much heat will be consumed by this liquid, right? and the sum of these two will be equal to 3600 joules, which is provided by the heater. Okay, so now we can write our equation very simply. So 3600 joules is coming, out of which 151 is taken away by the calorimeter. So the remaining one is going to be 3449 joules, right? And that is available to be taken by the liquid, right? So 3449 joules will be equal to 0.310 into CL, which is what we have to find, and 4, right? Joules. Now we can find the CL. The CL is going to be 3449, which is a specific heat capacity of the liquid, right? So this is our specific heat capacity of the liquid. Okay, so 3449 divided by 0.310 and then divide by 4. Okay, so if you do the maths, it will end up with 2781 joules per kilogram per Kelvin. So write it in scientific notation with 2.78, right, into 10 to the power 3 joules per kilogram per Kelvin. Okay, so like that, you can solve this problem. It's very simple. You just have to know from where the heat is coming, where it is going, who's going to consume it, and always the energy conservation is valid. Just make it equal to find the unknowns, and this is how we solve calorimetric problems.